Good day, stats enthusiasts. Welcome to this AI-assisted learning session. Today, we'll explore a powerful statistical tool, the Kruskal-Wallis Test. If you're ready, then let's begin.
We have here our presentation, Data-Driven Decisions, Kruskal-Wallis in Action, specifically focusing on a simple guide to understanding and applying the Kruskal-Wallis Test, examining whether the educational qualifications of IP teachers, bachelor's, master's, or doctorate, impact student academic performance. It highlights how statistical analysis can inform teaching-related decisions in diverse classroom settings. Before we begin, let's outline our objectives for this session. By the end of this micro-teaching, you should be able to understand the test's assumptions and requirements and learn how to run the Kruskal-Wallis test using Jamovi and interpret the results to make decisions.
Let's start with the fundamental question. What is the Kruskal-Wallis? The Kruskal-Wallis is a non-parametric statistical, sometimes called the Kruskal-Wallis H-test. It's a tool used for comparing more than two independent samples. Now, you might have heard of ANOVA, the analysis of variance. The Kruskal-Wallis is kind of like ANOVA's laid-back, non-parametric cousin. While ANOVA looks at whether there are differences in the means between groups, the Kruskal-Wallis takes a slightly different approach. Pretty cool, right? All right, let's talk about something we all care about. Student success. Have you ever wondered, does who teaches a student impact how well they learn? Specifically, when we look at our Indigenous peoples, IP teachers, and they come from different educational backgrounds. Maybe some have a master's, others a bachelor's. Does that actually make a difference in their students' academic performance? That's exactly the question we're tackling today. We're using the Kruskal-Wallis test to dig into whether IP teachers with varying educational qualifications lead to different academic outcomes for their students. Let's find out what the data might tell us.
Okay, so to answer our question, we've collected a bunch of data. When we first look at it, it often comes in a raw format like this. You can see individual teacher IDs, their qualification level, and then the student's academic performance score. Imagine having hundreds, even thousands of these rows. Now, we can't just throw this raw data directly into our statistical software like Jamovi and expect it to make sense right away. We need to summarize it first. This gives us a much clearer picture of our groups and how they compare. So after some careful organization, this is what our data looks like when it's ready for analysis. Our independent variable here, the educational qualifications of our IP teachers with 3 distinct groups. And for our dependent variable, the student academic performance, this is where we'll be comparing the median ranks across these teacher groups. This setup perfectly aligns with the requirements of our Kruskal-Wallis test. So to quickly recap the main requirements that make the Kruskal-Wallis our perfect tool for this specific data, we have at least 3 independent random samples, our teacher qualification groups. Our independent variable is categorical, with 3 or more independent groups, again, our teacher qualifications. And our dependent variable is continuous, which is student academic performance. Our data fits the criteria. Therefore, Kruskal-Wallis test is ideal for telling us if there's a significant difference in student performance across those different teacher qualifications.
Let's have first our hypotheses. Null hypothesis. There is no statistically significant difference in the median academic performance of students taught by IP teachers with bachelor's, master's, or doctorate degrees. While, for our alternative hypothesis, at least one group of students has a statistically significant different median academic performance compared to the others. Additionally, as our decision rule is based on an alpha level, for instance, 0.05, if p is less than the alpha, we reject the null hypothesis. If p is greater than or equal to the alpha, we fail to reject the null hypothesis.
Now let us go to the exciting part. Open Jamovi. Click the hamburger menu, select Open, and then browse to locate and open your file. Before we jump into the Kruskal-Wallis test, it's crucial to explore our data and check if our assumptions are met. This will help us confirm why the Kruskal-Wallis test is the appropriate choice. Next is, go to the Exploration tab and choose Descriptives. Then, drag average score into the variables box and qualification level into Split By. This will display the mean, median, standard deviation, minimum, and maximum for each group, bachelor's, master's, and doctorate. In the same descriptives window, click Statistics, check Skewness, and Shapiro-Wilk test of normality. As we can see, our skewness analysis reveals varying levels of asymmetry across the groups, with doctorate degrees showing strong left skewness and master's degrees exhibiting moderate to strong right skewness. Crucially, the Shapiro-Wilk test for all educational attainment groups resulted in p-values below 0.05, violating the normality which justify the use of Kruskal-Wallis test. Next, for a visual check of normality and outliers, we'll generate histograms and QQ plots. Now, let's select them. Looking at the 3 histograms, we can observe the general shapes of the distributions for average student performance. It doesn't appear perfectly symmetrical, suggesting it is not a normal distribution. In our QQ plot, while generally following the line, there are some noticeable outliers, particularly at the tails, which reinforce the idea that our data might not be perfectly normal. Recall from our earlier discussion that if your data is skewed or has outliers, the Kruskal-Wallis test is a suitable option. Given these observations, we can confidently proceed with our Kruskal-Wallis test. To do this, go to the ANOVA tab and select One-way ANOVA Kruskal-Wallis. Set average student performance as the dependent variable and qualification level as the grouping variable. And do not forget also to check the effect size box.
Now let's interpret the result. As you can see from the table, we obtained a chi-square value of 12.9 with 2 degrees of freedom. The most crucial part of this result is the p-value, which is 0.002. Since our p-value of 0.002 is less than 0.05, we can conclude that there is a statistically significant difference in the average student's performance among the different qualification levels. Also, our effect size value indicates a large effect. In simpler terms, the performance of students is not the same across these 3 educational attainment groups. Therefore, to pinpoint exactly which pairs of groups have significant differences in average students' performance, we need to proceed with a post hoc test. This next step will allow us to conduct pairwise comparisons and identify the specific groups that are significantly different from each other. Let's check the DSCF pairwise comparisons. The table shows us the p-values for each unique pair of educational attainment groups. Since the groups, bachelor's versus doctorate and doctorate versus master's, obtain a p-value greater than our alpha, it means that we do not find a statistically significant difference between them. Now, let's focus on the result that reveals the significant overall difference observed in the Kruskal-Wallis test primarily comes from the distinction between bachelor's and master's degree holders. This means that, among the groups studied, the performance of students with a master's degree is significantly different from those with a bachelor's degree. On our screen, we have our result written in APA format, which indicates a statistically significant difference. Practically, these findings suggest that teachers with higher qualifications may possess more advanced pedagogical skills or deeper subject matter expertise, which could positively impact student learning. Overall, the evidence strongly supports the notion teacher qualification level is a crucial factor in student academic success, suggesting that initiatives focused on enhancing teacher qualifications could directly contribute to improved student performance. We hope this guide has provided you with a clear understanding of the Kruskal-Wallis H-test and its application in Jamovi. We have our references here, and for questions and feedbacks, kindly pause this video and scan the QR code. Thank you for joining us today.
Until next time, in another exciting episode of non-parametric testing, dear stats enthusiast.